Okay, hi. So how do we find G, the estimators, the least square estimator or the maximum likelihood estimators? We'll do the same thing. So we'll just write what they are just to see, so we can see it again. So note LS, least squares estimators, are G equal to, say, G0, G P minus 1, dot, dot, dot. That, such that when gamma equals G, those are vectors, Q yi minus f. Now I don't know what specific form I have here, so I just write f. Xi, I don't know if I have multiple predictors or just one, so I'll write xi like this, but I can think of this as a vector. And gamma, vector, vector, scalar. So this is a scalar, and squared, right? So G is equal to D. It's just that when gamma is set equal to G, Q equal to this is a minimum, right? Okay, so this is how we will find gamma, okay? We want to minimize this. We'll talk about some ideas for how to do that, and we'll look at one cool way to do it, and it's the way, one of the ways R does it. Note this is the same. This is equivalent to maximizing the likelihood L gamma given X and Y, given the data. What gamma gives you the highest likelihood for your N estimates? This would be equal to, right, the product I equal 1 to N, 1 over square root 2 pi sigma. And this is normal, right? Because by the model, it's just a constant plus a normal piece. So the whole likelihood is normal. EXP minus 1 over 2 sigma squared. The variance is sigma squared, and the mean is, the mean would be yi minus f, the regression function, right? If I take the product there, I get, this is a big constant, right? So I have 2 pi sigma squared to the n over minus n over 2, exp minus 1 over 2 sigma squared, summation 1 to n, yi minus f xi sigma squared. And you see that minimizing this is Q. This is Q, right? So we see that minimizing Q, this is positive, and this is negative. So the smallest positive number here will make the likelihood the biggest. So we see, so minimizing Q is equivalent to maximizing L. Okay, so they're the same, and that's even more evidence that we should pursue it. Anyway, it's so cool that you're going to think, you're going to like it, that this is the way, this is what we use to do these. So let's see. All right, so suppose, where the hell am I? Where's my notes? Okay, I guess I don't have. All right, so how do you minimize Q? I think Q is easier, right? We don't have to deal with this. We have this, and it's the same thing. So we want to minimize Q. So how do you minimize Q there? Well, before, when it was linear, we used the beautiful orthogonal theory that said if I find the orthogonal projection into the span of the columns of the predictors and the one vector, then that was it. That was the target. And we could get beef from there. But you can't do that now. These are nonlinear, out of control. I don't know. We're totally lost, even with the simplest nonlinear F. So instead, we just use the more mundane direct approach, which is calculus. So to minimize Q, but we're not done there. That would be easy, right? That was it. To minimize Q, we set the partial derivatives equal to 0. Okay, so we set dq d gamma 0 equal to dq d gamma 1. And sorry, this should be p minus 1. And solve these. This is actually p equations up here, right? That each one is equal to 0. I just wrote it this way to save space. So we solve the p nonlinear equations numerically, right? Numerically with a computer algorithm. Now, it's quite crazy. I don't even know if, now I'm doubting whether I should even do it or not. I think maybe writing maybe a couple steps out might be useful. So for example, yeah. So let's actually compute one. So for the case, so note, so we have dq dk, we just do it, dq d gamma k, is equal to, so this is d gamma k summation yi minus f xi, the vector gamma, the vector xi, squared 1 to n. So I need to take the derivative here with respect to the kth gamma that's in that vector. Okay, well, the chain rule, right? Chain rule, I get sum 1 to n. This minus sign comes out, the 2 comes down, so I have minus 2 yi minus f xi gamma. And chain rule, what's the derivative of this? Well, we don't know. It's just the partial derivative, df xi gamma. This is the vector. All the gammas are involved over here. D gamma k. Okay, so that's the case one. And we need to set that equal to 0. Okay, so we do this. So we do this for all p parameters, and we have p equations. Okay, so we set this equal to 0. Set this equal to 0. So so we have this is the derivative. So we want to set this equal to 0, and then I would set gamma where it is equal to g. So setting gamma equal to g and dq d gamma k equal to 0 gives us, I just simplify a little bit, I have summation. The 2 can get thrown away because it's equal to 0. The negative can get thrown away. So I have 1 to n. I have yi. I have df xi. I'm leaving it gamma because it's a function defined as gamma, and I'm thinking of g as an actual value that I'll solve for. So d gamma k, and I'll evaluate at gamma equals g, and minus summation f xi. Now this I can just put g in, because this is just computed somewhere. And here I have df xi gamma over d gamma k. And this is also evaluated at gamma equals g, the vector, and this whole thing is set equal to 0. Okay, so I have to do this for p equations, okay, and each one has these sums too. These are very big. A lot of terms and a lot of equations, so we end up with, I don't know, however many. You want to count these, it's like 2n terms per equation, so it's like 2np different terms like this in these equations, p equations. It's complicated. So I actually did one and did an example of one. I am now doubting whether to do it. I'm definitely not doing it right now. Maybe we'll do it later. It's cool to actually see it. You shouldn't be scared of it. When you see it like this with the summations and the partial derivatives, you can't really tell what's going on. If you actually put a simple example in and do it, you see you get a real function with G0 and G1 and maybe more and some numbers. But it's very hard to solve. You couldn't solve it by hand at all. So this is what we're dealing with. Okay, so that's the end of that lecture. Maybe I will do it in the next lecture.